So today we're going to continue with our talk about function rules, tables, and graphs. We're going to learn two new words, continuous, discrete, and we're going to take this out to the real world. So our objective for today is to determine if a function is continuous or discrete and to graph real world functions. However, I'm going to start with one example, kind of tying into our last lesson, but kind of going backwards. So let's start with that one. So in our last lesson, we talked about if you were given a function rule, we talked about how to make a table. The five idea kind of came in, but we also talked about that sometimes negatives would not be great choices for inputs. And this is an example of a real world graph where you wouldn't have negative gallons. But we created a table, we graphed the points, we connected and extended and talked about all of that in our last video. Now what I want to do is I want to give you a graph and I want to go back to looking at points, like pull points off the graph using function notation. And we're also going to talk about, or continue to talk about, interval notation for domain and range. So let's start just kind of a recap of the last lesson, but looking at it from sort of the other perspective. We want to know what is f of 3. Now we don't have a function rule where we can substitute that 3, so we need to look on the graph. You're going to remember that that 3 is your input. That's your x. So we're going to go along the x-axis and find 3 as the input. And if we come up and hit the graph, you can see that the output would be 4. This point would be 3, 4. So f of 3 would be 4. How about if you stop a second, what would f of negative 4 be? So once again, if we come out to negative 4, come up, hit the graph, do you see? And did you say that that would be 6? Okay, so now this is different. This is asking what x would give us an 8. So what x gives us an output of 8? So now we need to look at the y, the output. And if you look here, wait a minute, which way do I go, right? There are two answers. There's 5, 8, and there's also negative 5, 8. So there are actually two x's that would give me an output of 8. And if you go back to thinking about, well, I'm going to give it away. This is an absolute value function. That v tells me that if I was to write a rule for this, it would be an absolute value. Remember that we talked about that there can be two kind of answers, and we're seeing that negative 5 gives us an 8 and positive 5 gives us an 8. Now, what would the x be for f of x equals 0? Your turn. Okay, so if I go to a y of 0, there are again 2 points. There are two x values that give me that y, and they would be negative 1 and 1. Negative 1, 0, and 1, 0. So let's talk again about how do we look at a graph and determine domain and range. We're going to remember that domain is the set of all inputs. So we want to know what numbers can go into this function. And if we look at it, because of the arrows, I want you to picture that this v is going to continue getting wider and wider and wider forever. So eventually there would be a 9 comma something, and eventually there would be a 1000 comma something. So every number is going to go in because of, every x would get covered by the graph. So the domain in interval notation, why don't you stop and think, how would you write that in interval notation? So if we're talking about all numbers going in, our interval notation would be negative infinity to infinity. Every number can go in as an x. Now the question for range is what numbers can come out? And you kind of have to turn your head now and look at it from the y perspective. What y values are represented on the graph? See if you can think about that one and write your answer in interval notation. The minimum y, see, the y of negative 9 down here never comes and never hits the graph. So the first y is actually negative 2. That is our first y. If you turn your head, that is the first y. And then every other y will be covered by the graph as it goes up and up and up and up. So it would be inclusive, the bracket, negative 2 to infinity. And that's the numbers that come out. So you can see how interval notation is really kind of handy when writing the domain and range off of a graph. Okay, so now let's talk about this idea of these two new words, discrete function and continuous function, and let's take this to the real world. So discrete and continuous data. Discrete data usually involves a count. It's a number of people or objects. Continuous data usually involves a measurement. It's like temperature, the length of something, or weight. Basically, discrete data, if I was standing in front of you right now, I would be doing kind of jumping. It jumps from one thing to another. It isn't a smooth through every number kind of feeling. So if you think about it, if you're counting the number of people in a room, for instance, it would be one and then it jumps to two and then it jumps to three. When it goes from one to two, it doesn't go through every number in between. There's not 1.1 people or 1.9 or 1.5. Now, continuous data is going to go through all of those numbers in between. So as the temperature rises, let's say outside on a nice summer day, and it goes from 80 degrees to 81, it didn't instantly go from 80 to 81. It went through every temperature in between. So here's kind of an idea of a graph, a pictorial representation of what we just said. So the number of people in a restaurant, you can kind of see, would jump. You wouldn't connect these dots because there was never 6.2 people in the restaurant. And that's why you got this kind of jumping picture. However, the temperature in the restaurant, as it rises and then later on falls, it will go through all the temperatures. It's not a measure that it has fractions and decimals. That's not what tells you whether it's continuous. It's the idea that it has to go through all the numbers in between. So let's take a look at this and just decide if this data would be represented by a discrete or a continuous graph. Would we leave the points separate or would we connect them? So the number of cars passing a traffic light, would that be discrete or continuous? With the number of students buying lunch each day. So what I want you to do is go down these, I think it's 9, and put a D or C, and in a second we'll come back and see how you did. Okay, let's check and see how you did. Number of cars passing a traffic light should be discrete. Number of students buying lunch each day should be discrete. Now, as the water in a swimming pool either evaporates or you fill it with your hose, that would be continuous. It doesn't jump from one depth to another depth instantaneously. A wrestler's weight during the season would also be continuous. The number of points scored in a basketball game would be discrete. The height of a plant as it grows in your garden would be continuous. The speed of a race car would be continuous. The number of fish in a fish tank, discrete. And student scores on a test would also be discrete. So even though you might see on a quiz like a 78.5%, and you say, oh, well, there's a 0.5, you can't get like a 79.023. So we jump kind of, at least in my class, by half points. So that would be discrete. Let me show you that again in case you missed it. There are sort of the answers that we just talked about. So basically, if you have a discrete graph, you wouldn't connect the points. And if it was a continuous graph, you would. But I've just kind of lied to you a little bit because even if it's a discrete graph in a real world situation, we'll often connect the points so that we can make predictions based on a line or curve that we put in. So even though it might represent a discrete count of something, if we want to predict what's going to happen way out in the future, we would have to add that curve or that line to be able to make that prediction. But generally speaking, a discrete graph is going to be not connected in a continuous way. So what we're going to do now is we are going to create a graph from real world data. We're going to do this on a piece of graph paper. So again, you will have that in the classroom. We're not going to use the coordinate graph paper. In a second, I'm going to explain why we're going to use regular graph paper. And the graph that we're going to make is going to be of your heart rate based on your age, basically. And I go out, and you could imagine that I go out and I take samples of people that are 15 and 25 and 40, and I get these average beats per minute over here. And as you can see, as your age goes up, your beats per minute is going down. It's because you're dying, right? No, I'm just kidding. But yeah, your heart rate does slow down over time. So, who is the X and who is the Y? That's the first thing we have to determine when we go to make this graph. We need to know who is the dependent and who is the independent variable. And in this particular case, think about it. I don't come up and take your heart rate, take your pulse, and then say, oh, you have a certain pulse, so your age changes based on that. No, but your pulse rate will change based on your age. So your beats per minute depends on your age. So this beats per minute would be your dependent or your Y, and your age would be your independent and your X. And if you think about it, oftentimes, not always, but oftentimes your X, your independent, if there is time involved, it is often the independent. There are exceptions to that, but that is sort of the rule. So the target rate depends on your age. So the heart rate is dependent, and the age is your independent. Well, now we know kind of how to set up our graph, at least initially. So in creating a graph, this is probably the most important slide today. This is what you need to have on a good real-world graph. And the first thing is a title. A title gives you an idea of what the information is in the graph. And oftentimes, if I give you a graph without a title, you have no idea what the data is you're looking at. And as important as it is, it's the most missed thing. So please remember to kind of start by putting the title there so you don't forget. Then you're going to make sure that your independent variable is going to go on the X, in this case years. Your dependent is going to go on the Y, in this case beats per minute. And you're going to label your axis, and you're going to make sure that the units are there. Then we have to create proper scales. And when we make a proper scale, we need to make sure that each block on the graph paper represents the same amount. So we're not going to jump from 1 to 3 to 15. Each block needs to represent the same amount. Now you can have different scales on the X and the Y, but once you start a scale and say, oh, well, this block is going to be 2 on the X, then every block has to represent that same amount. And you kind of want to start by looking at your minimum and maximum. So if you look at your beats per minute, we don't have one on our table until we're in the 120s. So in this particular case, it would be okay to put a break in the graph. When you do put a break in the graph, it's good to indicate it, and it's also good to look for those because it can distort the graph. You have to be aware that it exists. And then again, I just mentioned that the intervals are equal, okay? And you want to pick intervals that are easy to plot and read. So the intervals we often pick are by 1s or 2s, 5s, 10s, things like that. An interval of 3 or 7 or something like that is really hard to read, and it's very hard to plot. So we want to make nice sort of scales. Then you're going to plot your points. And oftentimes, based on your scale, it's kind of an estimate of where they go. They're not always going to go on the lines. And then you have to decide whether to connect or extend. And we're going to remember that sometimes, even on a discrete graph, we will put a line or something in there so we can make predictions on a real world graph. So let's take a look at this. So I'm just going to kind of show you here. So what you would want on a piece of graph paper is the first thing I notice is that I'm only looking at quadrant 1. Remember, there's 4 quadrants when you're looking at the coordinate plane, and I'm only looking at quadrant 1. And the reason is there's no negatives here. You're not going to have a negative age, and you're not going to have a negative heart rate. So I'm only using the first quadrant, and that's why you don't want to use the coordinate graph paper, because first of all, it's extremely tiny and limiting, and 3/4 of it you're not even going to use. First thing I would do is get that title up there to explain what the data is. And in this case, I'm calling it target heart rates versus age. Remember that we said that on the X was going to be our age in years and Y was going to be our target heart rate. So I would get that in there, including my units. Put those labels on. So at any point in time here, I would be asking that you're making this graph kind of along with me. You can pause this just as you draw in what you need. The next thing we're going to do is we're going to put the scales on here. And what I meant by even intervals is you'll notice that each block here is worth 5. So 5, 10, 15, 20. Now you don't have to write each number. You'll see I'm kind of skipping every other number, but each block represents 5. It's an even scale. This little guy is a break in the graph because remember when we looked at our data, we never go below that 122. So I actually started at 110. And then as I'm going up here, you'll notice that 2 blocks represents 5. So this would be 115. 2 more blocks is 120. 2 more blocks is 125 and 130. And that's what I mean, again, by an even scale. So we put our title, we put our labels, putting the correct data on the right axis based on dependency. We create our scales. And once you've kind of done that, you're ready to start plotting the points. So again, here, this is just talking about, why I'm putting the break in here, and again, why I'm doing by 5s there. So now it's time to plot the data. So when I go to plot the data, and this is where I mean where it can be kind of an estimate. So I'm going to go 15, and when I go to do 143.5, it's a little bit less than 145. So when you're plotting these points, they're not going to be plotted necessarily right on horizontal, vertical, or in the crosshairs of two, horizontal and vertical. So here are my points. I just plot those. And now would be the question, do I connect and extend? What do I do here? So in this particular case, your heart rate would be a continuous. So I'm definitely going to connect on this. And it looks to be pretty linear. So I'm going to get my ruler out and I'm going to draw that line and I'm going to put my arrows on both ends. Now, you might say, well, we can't go into the negatives. First of all, remember there's a break here, which I forgot to draw on this particular slide. So this is going to keep going down. And yes, at some point, this is going to hit the y-axis, and then it would no longer extend into negative age. But right now, for what I can see, I should extend it with an arrow on each end. And that's how we graph a real-world example. So again, I just want to go back to this slide and remind you that this is the key to making a really good real-world graph. And the time really comes in setting it up properly. And once you've got it set up, the plotting the points and drawing the line or curve or whatever it might be is pretty easy. So, put that time in ahead of time. So today we talked about really 3 ideas. We started with a backup of what we did last time, kind of backwards into here's a graph. How can we pull points off? We looked at finding the f of x and then finding the x and then domain and range, which we will continue, I promise, to talk about. Then we talked about whether something was discrete or continuous. And then finally, we did one real-world graph. So it's kind of your turn to give this a practice. Really important stuff today. And we will continue to use all of it, I promise, as we go forward. Have a great